Hello, class. We are going to continue our discussion on pKa's and acid-base chemistry here. And the first thing, or what I want to talk about here, is let's say we have ethanol, and we compare that to isopropyl alcohol, like that. Now, we've learned that we have pKa tables that will tell us the pKa of these alcohols. However, the tables in your textbook are very limited in scope because there are, who knows, like just so many molecules out there that you cannot have a pKa table for every single molecule out there. And so how are you going to know what a pKa of an acid is when it's not on a table? One way you can do that is you could go to the table and find, let's say this is the molecule that we want to find the pKa for, right there. But when we go to our table, that molecule is not there. So how can we get a rough estimate of what the pKa of this alcohol is? Well, what we do is we go to our table and try to find a molecule that resembles the same functional group. So we notice that this is an alcohol. So we will go to our pKa tables and find an alcohol. And then we will try to find an alcohol that the structure resembles our structure resembles the molecule of interest. And so we go to the pKa table and we see, hey, ethanol looks very similar to isopropanol. Clearly they're different, but similar. So we go to the pKa table and we find that this guy has a pKa of 16. And so we can look at this molecule and say it is approximately 16. And so that is what you're going to have to be able to do when you go and you see a molecule that's not on the pKa table. You need to find something that's very similar. And then you can say it's roughly 16. When we actually calculate or do the experiment to figure out the pKa of isopropanol, it is 16.5. But will you know 16.5? No, you won't, because it's not on your pKa table. So that's one way to do it. Another example would be, let's say we have benzoic acid. Okay, there's our benzoic acid. What is the pKa of that guy? It's not in the pKa table, so we got to go to the table and find something that looks similar to this. And so when I look at this molecule, what functional group do I have? A carboxylic acid. So you're going to go and find a carboxylic acid. And the one that may pop up on your table is acetic acid. And acetic acid, looking at my notes here, has a pKa of 4.75. So you could say benzoic acid has a pKa of approximately 4.75. Do you see what we're trying to do here? Okay. But then this is an approximation, but you're going to run into situations where this strategy does not work. Okay, so for example, you could have a molecule that looks like this. What if we had a molecule that looked like this? Okay, so that's TFA. No, that's not TFA. So when we look at this molecule, we're like, hey, what is the pKa of this? And we look at the molecule and we say, hey, the functional group here is a carboxylic acid. So we would be like, hey, go to our pKa tables and we'll find, hey, acetic acid. It has the same functional group as this. And then we're like, okay, the pKa table says it's 4.75. So we would approximate this to be 4.75. But this is not a good approximation because the real answer for this guy, the pKa, is 0.77. Do you see how they're not similar at all? Well, why does this one not work? Well, because we have different atoms here that they're not carbon and hydrogens. Typically, when you have an acetic acid, or sorry, a carboxylic acid of sorts, the alkyl chain doesn't change it too drastically. But the moment you start adding electronegative atoms like chlorine, fluorine, or anything, it's going to mess it up. So what we have to do now is the pKa table is very, very limited. So the better way to approach figuring out what a pKa is, or a rough estimate of a pKa of acids, is to learn some guiding principles. And it's these guiding principles that will help you to compare if you had, let's say, acetic acid versus this guy. The pKa tables aren't going to help you very much, okay? Because these other atoms right here. So I'm going to teach you these guiding principles that won't actually give you a hard, fast number of what the pKa is for this molecule. But knowing the principles, what you can do is look at these two molecules and say, this one is more acidic than that one. You don't have a pKa table. So we're going to learn principles that we can apply when we don't have a periodic table, or sorry, a pKa table, or when the pKa table doesn't help us. We'll use guiding principles, okay? So what we're going to take a look at is those principles, okay? So let me clean up this board and we can get started. Okay, so here are the principles that we are going to discuss. And these principles are going to be able to help you determine, when you look at this amine and this amine, which one is the most acidic. And we're going to use this acronym here called the cardinal rule to help us figure out which one of these is the most acidic. So what we have here, I'm not going to write it out, I'll just talk about it. So the cardinal rule stands for the principles that we need to learn and apply to situations like this. C stands for charge. A stands for atoms. RD, so that's one. We put those two together. Okay. R is for resonance, and D is for delocalization. Okay. And the IN right there stands for inductive effects. So you learn about resonance in Gen Chem. You've learned it in my class. You've learned about induction in Gen Chem, and you're going to relearn it with me. But we're going to apply these principles to help us figure out what's going on. So we're going to start with the charges. Okay? So there's this general idea, general principle, that when you have, let me get to it here so I can say it accurately. So here's the principle. These protons right here. The proton is more acidic when it is attached to an atom that has a positive charge on it. So you see here's this hydrogen is attached to a nitrogen which has a positive charge. This hydrogen is attached to a nitrogen which is neutral. So based off of that principle, this molecule right here is going to be more acidic because the hydrogen is attached to an atom with a positive charge. Now, when we go and look up the pKa's here, we will see that the pKa of this amine is 36, and the ammonium right here is 9.4. So those are the pKa values that we can find on the internet. And we can see that this is clearly the most acidic. So what is it about charge that determines if something is acidic or not? Well, we can look at it energetically here. So I'm going to draw an energy diagram here. And let's take a look at, keep this all color-coded here. When you have reactants that are neutral, they're generally low in energy here. So we will say that's our NH3 plus water. Right? Generally lower in energy. And when you have a reaction here with a positive charge somewhere in the reaction, that's going to make it higher in energy. And so that's where our NH4 is going to be plus water. Okay? So it's higher in energy. That's our y-axis here. Higher in energy. And so what's going to happen is that when you do this reaction here, do you see what mechanism we're using? Our water's the base, the ammonia is our acid. And so what's going on here? It's a proton transfer reaction, proton transfer mechanism. Now what happens is when this reacts, it's going to have an energy activation here and be, let's redraw this here. Will look something like this. And so over here, that would be our products right there. And let's see here. We want to get this right. All right, and that would be our NH2 minus plus H3O plus. Okay. So when we look at these energy diagrams here, what can we see? On the reactant side, right here, we can see that the positively charged species are higher in energy. On the product side, on the right, we can see that this in orange has a positive and a negative, so two charges. That's why it's higher in energy than this one in pink, because this one has a neutral and a positive. So it's slightly lower in energy. And so the reason why this guy has a smaller pKa or is more acidic is because look at the energy diagram here. Look at that energy of activation right here. The energy of activation for the pink line is only that tall. So it can go over that hill a whole lot easier than if you take a look at the orange one, and you can see that it is from there to there, a much bigger hill to climb. And so this proton is influenced by the energetics of the system. This proton's like, hey, yeah, it's easy to take my proton. Take it. take it. It's fine. Whereas this guy's like, I like it. I'm low in energy. I'm okay with it. Please don't take it. And it has a much harder time giving it up because it has such a high energy of activation. It just takes a lot of energy to rip that proton off. All right. So that's the first thing that we need to understand, is that charged species are going to be higher in energy. Okay? And when you look at a positively charged atom in the reactants, we can see it's going to be higher in energy, easier to rip off the proton, and hence makes it more acidic. Okay, so let's take a look at a different idea now. So what we have here are some molecules here with their corresponding pKa's. And you can see methane right here has the largest pKa and hydrofluoric acid has the smallest pKa. So that makes hydrofluoric acid the stronger acid. Now we could condense this to just looking at these atoms right here. We could look at it like this. When you go to your periodic table, notice that this is the order in period 2. You see carbon, nitrogen, oxygen, fluorine in that way. So what we can do is make this general idea here when looking at these molecules here, that as you go further to the right, you're going to see that the acidity increases. So pay very close attention. What are we talking about? We are comparing the acidity of this proton and that proton. And as you go further to the right on the periodic table, when you're comparing acids in the same period, you can see carbon, nitrogen, oxygen, and fluorine are all in the same period. You can make this general principle here, or general statement. But we want to understand at a deeper level why this is the case. You can memorize trends, but if you can learn principles, then that is going to save you a lot of hassle. So what if we have this? I'm going to write out 2 reactions on the board, and then I will come back. So what we're going to take a look at is we're going to compare methane and ammonia and look at their pKa's. Well, we already know their pKa's. We already know ammonia is more acidic, but we want to understand why that's the case. So what you can do is you can look at this reaction and this reaction in the reactants, and we can see they're all neutral. So we can draw a energy right there, and we can say, hey, that's going to be both of them. So we have NH3 plus water, and then we have the methane. So what I'm trying to demonstrate here on this energy diagram is that because both of these reactions here are neutral in their reactants, they generally have the same energy level. Yes, this orange one is above and this one's below. That's not what I'm saying. Both of these reactions are on this green energy level because they're neutral. And yes, we are making an assumption, but it's okay to make this assumption that when you have different species, but if they're all neutral, they relatively have the same energy, okay? Now, if we expand out our table here, let's expand that out. When we look at the reaction of ammonia, what do we see? We now have positive and negative. We have charged species on the product side. But whenever you have a charged species system here, they're going to be at different energy levels. Only when they're neutral do we assume they are at the same energy level. But when they are different molecules with charges, there's going to be a difference. And what we see here is the nitrogen. It's going to be about here. So that's our NH2 minus plus water. And then this is going to be right here, CH3 minus plus water. Not water, hydronium. There. So what we have going on here is an energy diagram that kind of looks like this. And then the blue curve like that. So what do we see in this energy diagram? We can see that the conjugate base for ammonia is lower in energy than the conjugate base of methane. So you can see that ammonia here is going to be more acidic, more willing to give up its proton, because look at the orange curve. It has a lower energy of activation, so it's easier to get rid of that proton. But then it begs the question here, how did I know this conjugate base is higher in energy than this conjugate base? How did I know that? Okay. Well, I will get to that in a minute, but let me make one statement here that you need to write down because it's really important. When you are comparing two acids and you want to know which one's the most acidic, what you do is you figure out their conjugate bases. So here we have our ammonia and our methane. I draw out what their conjugate bases are. Okay? And the conjugate base that is the most stable is going to give you the most acidic molecule. So when I look at the energy diagram here, comparing these two conjugate bases, I find that this guy right here in orange is lower in energy. So it's a more stable conjugate base than this one. So that means, because this conjugate base right here is more stable than that conjugate base, makes the acid right here more acidic. So let me read it to you one more time. So when comparing two uncharged acids, the stronger acid is the one whose negatively charged conjugate base is more stable. That is a true statement. Now let's talk about why and how do I know that these two have different energy levels, even though they have the same charge. The answer to how do I know this guy is higher in energy than this guy is because of electronegativities. So on the periodic table, what is the most electronegative atom? It's in the top right corner, it's fluorine, right? And so what we have going on here is that when you look at the conjugate bases from the four acids that we're looking at, the atoms here, the electronegativity increases as we go from left to right. So this is more electronegative. as we go towards the fluorine. And, okay, so what? So what if the fluorine is more electronegative than the carbon? Well, it comes down to stability. If this atom is more electronegative, it can endure, or it likes, a negative charge better than an atom that has a smaller electronegativity. So because fluorine has a higher electronegativity, it can tolerate the negative charge. And if it can tolerate the negative charge, then it's going to be lower in energy. And that's exactly what we're seeing here when we compare ammonia and methane. We look at their conjugate bases, and when we look at how stable their conjugate bases are by invoking electronegativity. Nitrogen is more electronegative than carbon, hence this conjugate base is lower in energy, more stable, which then makes the acid more acidic. Isn't that pretty cool? So what we can also say when we go from left to right is that these anions are more stable. Pretty slick. So that right there is the guiding principle. Okay? Next, I want to show you how to do this analysis when acids are positively charged. Okay, so what we're doing here is we're comparing two acids, our hydronium and our ammonium. Sorry. You can see they're both acids, they both have a positive charge. So which one between these two is the most acidic? Well, here's the statement on how to do that. When comparing two positively charged acids, the stronger acid is the one that is less stable. So now what we're doing is we're looking at the reactant side and finding out which one's the less stable. So if we take a look at hydronium, okay, and we'll just put hydronium right here, okay, that's our H3O hydronium on the reactant side. Now, where would I put ammonium? Where would that be? Would it be higher in energy than hydronium or lower? Well, we use the same principles of electronegativity. We can see if we look at the trend, it's carbon, nitrogen, oxygen, fluorine. It's more electronegative to the right. So we can see that the oxygen is more electronegative than the nitrogen atom. So that's what we're comparing, this oxygen and that nitrogen. I know oxygen is more electronegative. So electronegativity means it can and likes negative charge. What do we have here? We have a positive charge. So because oxygen is more electronegative, but has a positive charge, it's going to be more uncomfortable. More electronegative atoms don't like positive charges. So because nitrogen is less electronegative than oxygen, it can tolerate that positive charge a little bit better. So we can expect that the ammonium, NH4 plus, is going to be lower in energy than the hydronium. And then we look at the products here, okay? And we can see that both have hydroniums. So that kind of like just cancels each other out, right? So now we're just comparing this species and that species. And remember when we're looking at molecules that are both neutral, okay? They have relatively the same energy. Right there. So that is going to be the products for both reactions. So if we look at the energy diagram here, we can, I'm going to extend this energy diagram to right here because of how I drew it here. What happens now is we can have something like that. Okay. Am I doing the color code right? Yeah, okay. Got to make sure that's right. And then I'll extend the energy diagram over there. Okay. And then this could be something similar to that. Like that. Okay, now you're looking at that. And how can I say, hey, which one's going to give up its proton easier? Well, I look at the energy of activation here. And when you compare these right here, which arrow here is bigger? The blue one. So that means ammonia here is going to take a longer time to react, and it's not as reactive. So what can we say here? When you have acids that are positively charged, it is the acid that is the least stable that is going to be the most acidic molecule. All right? And that principle that is being taught here is due to an electronegativity argument. Oxygen is more electronegative, hence when it has a positive charge, it is that much more unstable and unhappy than a less electronegative nitrogen atom with a positive charge. Right? Now let's take a look. Previously, we were comparing acids in the same period. But now we are going to take a look at acids down the same group. So that's what we have here. What we have is hydrochloric acid and hydrofluoric acid. And we're going to make that comparison. So they're all, these two acids right here are in the same group. Now, proton transfer mechanism is the same. So what's the rule here? How can we determine which one is more acidic? Well, we can see that they're neutral acids. And so the rule says, look at the stability of the conjugate base, and the more stable the conjugate base makes the acid more stable. Or, sorry, more acidic. So let me re-say that so there's no confusion. When you're comparing these two acids, how do you know which one's the most acidic? You go to the conjugate bases and you say, hey, you have to make a decision which one of these conjugate bases is the most stable. If you say, hey, the chloride anion is the most stable one, then that makes hydrochloric acid the most acidic. Or if you said fluoride is the more stable conjugate base, then that would mean hydrofluoric acid is the stronger acid. So how do we do this? Well, what did we do when we were going in the same period? We used an electronegativity argument, right? So which one's more electronegative, fluorine or chlorine? You would say fluorine is more electronegative, so it can stabilize the negative charge better. So you would say, hey, hydrofluoric acid is the stronger acid. So let's pull out the pKa's from a book. So the pKa for hydrofluoric acid is 3.2. The pKa for hydrochloric acid is -7. -7 is a smaller number than 3.2. So that means hydrochloric acid is a stronger acid than hydrofluoric acid. So now, right now, you should be like, what's going on here? You teach me a rule and then you violate it in the next concept here. Okay, so I can see that this is a little confusing. But when I first analyzed this, I was using an electronegativity argument. I failed to look at the size argument. So when we have the fluoride anion right here, it's relatively small. But when you look at a chloride, it is larger. And so now we have a size argument that we have to rationalize here. Whenever you have a negative charge that's localized in a small space, it's going to be higher in energy. Whereas with a chloride anion, the charge has a much larger volume to move around in. And so that ability to move around lowers the energy of the anion. It's kind of analogous to, have you ever tried to, or have you ever babysat a toddler and you want the toddler to stay in one room in an enclosed space? They don't like that. They need freedom and space to move around, and they're generally more happy when they can move around. Same thing with the atoms here. When you have charges, if it's a fluoride, the charge is more localized and concentrated, whereas in a larger atom, the charge is delocalized or diffused away. It's just more space. So the idea here then is, when you're going down the same group on the periodic table, it's not an electronegativity argument. The size argument trumps the electronegativity argument. Okay? So let me conclude with reading the rule one more time. The stability of an anion tends to increase when the negative charge is on an atom farther down a column of the periodic table. So if we change this right here, what if I change this guy to Br, hydrobromic acid? We'll change that guy. Now, which one is the stronger acid, hydrobromic acid or hydrochloric acid? Well, the bromide right here is going to be what? Larger than the chlorine. So we could see something that looks like this. And so that would make the hydrobromic acid more acidic. And the exact pKa on hydrobromic acid, let's see if it shows here. pKa of -9. So that's 2 orders of magnitude more acidic than hydrochloric acid. So that's pretty significant. Okay, let's keep moving along. Now let's take a look at when you look at an alkane, alkene, and an alkyne. And what I'm going to do is I'm just going to draw an arrow down here to show the conjugate base. Okay. So this one. Now you can notice that what am I doing? I'm abstracting off 1 proton from these. So the general rule still applies when we're looking at the acidity of these guys. And that is, more stable, the conjugate base, means the stronger acid. So when we look at these conjugate bases here, we can say that this conjugate base is the most stable amongst the 3. And we can say that because we have the answer already before us. The pKa is 25 for this alkyne. So that means this hydrogen is the most acidic compared to these 2. So the pKa value just tells us that. But I'm teaching the guiding principles here, not by just looking at numbers. Why is this conjugate base here more stable than these two? Well, when we take a look at the cardinal rule, right? Cardinal. Well, let's just worry about these first three letters here. We can see charge. They're all the same charge, and they're all the same atom. So the atoms don't change. So how can we determine this guy's the most stable? Well, it has to go back to electronegativity argument. Okay, so electronegativity. But when we look, each atom here is a carbon. Okay, so how can I use an electronegativity argument here? Well, it's because it's a little bit different. It's called effective electronegativity. And effective electronegativity deals with when you're looking at carbons. And what is the hybridization state of that carbon? sp3, sp2, and sp. What happens is the sp is more electronegative than the sp2, which is more electronegative than the sp3. So that's saying the sp is more electronegative. But we don't use that word just electronegative. We have to say effective electronegativity. And since this conjugate base came from a sp, that means this negative charge is going to be more stabilized on a more electronegative atom. So this carbon here has a greater electronegativity than that one. And the reason why that is the case is because when we look at this carbon here, it is a sp. And an sp has more s character than a sp3. An sp3 orbital looks more like a p orbital, not exactly like a p orbital. And then the sp orbital looks more like an s, not exactly like an s, but more so. And so what that does is when you have more s character, the charge is going to be more localized on those carbons. So the charge is more localized. So it's more electronegative. It attracts the electrons. Whereas when you look at an sp3, the electron density is more dispersed. And so it's less electronegative. But when we're comparing the same atoms, all three carbons, we call it effective electronegativity. So the take-home message is that the sp hybridized carbons have a higher electronegativity than sp3, which means it's going to stabilize the negative charge on the conjugate base. And since that conjugate base is more stable than that conjugate base, it makes the acid more acidic. That's all there is to it. Okay. Okay, so let's just review the cardinal rules. We've been looking at charges. We've been looking at acids with different atoms in them. And now we have resonance and delocalization to look at. So if we take acetic acid and compare that to ethanol, like so, which one is the stronger acid? Well, if you've memorized pKa's, then you already know the answer. You know the pKa of carboxylic acids are about 5 and alcohols are about 16, so that's the stronger acid. But we are here to learn guiding principles. That is super, super important. So what happens here? That comes like this. We do our proton transfer reaction. And we're going to get that plus our hydronium, right? And so we'd have the same thing here, like that. And we have that many electrons. 1, 2, 3, 4. So let's put them there. Okay. Plus the hydronium. The guiding principle is just the same. We have to look at the conjugate bases. And we already know this conjugate base is more stable than that conjugate base because of the pKa's. We know that. But what's the guiding principle here? Well, it has to do with resonance and delocalization. We can take the carboxylate right here and draw a resonance structure. Now remember, with resonance structures, you have to draw that arrow that looks like that. And so this lone pair here can come like this. Oh, we got to put those there as well. And then we could have a resonance structure that looks like this. Like so. Whereas, can we look at this ethoxide and draw a resonance structure? Can we take these electrons and bring them in? And the answer is no, because you would form a Texas carbon. So that's a no-no. So what we have is resonance. And resonance is going to stabilize the conjugate base. Why? Because the electrons or the charge is delocalized. You see how the charge is right here? Now it's right there. That charge is going around the molecule. So that's what the D stands for, is delocalized. That charge is delocalized through resonance. And that's a stabilizing effect. Whereas this negative charge is localized. It does not move. It stays on that oxygen atom and does not move through the molecule. So that is a very, very important principle. Resonance and delocalization stabilize the conjugate base, which then, if the conjugate base is more stable, makes the acid more acidic. Well, let's wrap up the cardinal rule by looking at the induction effects. So if we take an alcohol, treat it with water, we could have an acid-base process go like this. Give us our ethoxide, okay? Plus our hydronium. But then we could take a look at, let's say, let's just replace one of these hydrogens on this carbon with, let's say, a electronegative atom like chlorine. There should be a plus there. So we could have the proton transfer mechanism. Negatively charged, there's our chlorine, plus our hydronium. So which one's going to be the most acidic? Principle is we look at the conjugate bases and figure out which one is the most stable. Now, when I look at the cardinal rule, I can see that the charge is the same. I can see that the atoms are the same. I can see that there is no resonance or delocalization. Those are localized charges. But now we have the last one, induction effects, which means that we can take an electronegative atom, and we know electronegative atoms are going to suck electron density towards itself. So as the chlorine is sucking electron density, the electrons in this bond right here towards itself, that will then make this carbon a a little bit more positive charge. So it's going to suck electron density from this guy. And then it's just a domino effect that this electronegative atom here is going to be pulling electron density towards itself. And so as that does that, it's going to stabilize that negative charge, because it's almost kind of like delocalization, almost, where that negative charge is filling a pull towards the electronegative atom. And so it's kind of moving, and so it's stabilizing it. And so since this conjugate base is the most stable compared to this one, that makes this guy the stronger acid between the two. Inductive effect, something that you saw in general chemistry. Okay. Now you can apply the same principle to, let's see here. Let me look at the example. Now let's take a look at this example. You see what I did with these molecules is I just added an extra hydrogen. When I added that extra hydrogen on the alcohol group, I generated what? A positive charge. Now the rules are a little differently now when we're looking at acids that have a positive charge. We're trying to find the acid that is the least stable. And the least stable acid is the one that's going to be the most acidic. And so we can look at these two molecules here and be like, which one's the most acidic one? Well, what's the difference between the two? There's obviously one difference, and that is the chlorine atom. So what does that chlorine atom do? Well, it has induction, right? So it's going to pull the electron density towards itself. So is that chlorine a stabilizing effect to that positive charge or a destabilizing? Well, when we were looking at it, when we were looking at this molecule like that, it was stabilizing because it was taking that negative charge and moving the electrons inductively towards the electronegative atom. That's a good thing. But now in this situation, it's positive. And so very little electrons. So now very little electrons, already very, very uncomfortable due to the positive charge, is now trying to be yanked towards the chlorine. And so that inductive effect now is destabilizing this positive charge because there's very few electrons over here, and this guy's trying to suck electron density towards itself when there's nothing to give. And so in this example, the inductive effects is destabilizing. So when we compare these two acids, this one's more destabilized or the most unstable, so that makes that guy the most acidic in that example. Yeah. Okay. So if you have any, so that's the rules for the cardinal rule. So if you guys have any questions or concerns, please feel free to reach out. Oh, before I end this video, what's going to happen now is all these examples that I showed you, we were looking at examples where we were only looking at one of the principles in the cardinal rule. But now what you're going to have to do is look at an array of molecules and use all of these rules at the same time. And that's what we will discuss later in class.